Dear students, in the today's lecture, we are going to discuss about quantum mechanics. What is quantum mechanics? Mechanics explains the motion of particles. Quantum means small discrete value. If we take a charge, the small discrete value exists for charge is charge of an electron. That is 1.602 into 10 power minus 19 coulombs. There is no charge value exists below this value. If we take any charge value, always integer multiple of this small charge, that is charge of an electron. That means the existing values are 1e, 2e, 3e, 1000 e. That means all are integer multiple of charge e. There is no value exist between 1e and 2e. Like that, if you take energy of a photon, that is E equal to h nu. H is the Planck's constant, nu is the frequency of the radiation. If you want to find the energy associated with any EM radiation, there is always integer multiple of h nu. That means the quantum value exists in case of electromagnetic radiation is the energy associated with a photon, that is h nu. So if you want to explain motion of such a microscopic particles, that is photons, electrons, how they behave, how they move inside a metal, or how they interact with the material, all those things, if you want to study, we are taking the help of quantum mechanics. So quantum mechanics explains the motion of microscopic particles. Here, in the microscopic level, the behavior of particles is very unusual. There is a weird behavior we are observing in case of microscopic systems. They are behave like a particle as well as a wave. That's why analysis is quite complicated to understand and analyze. So before going to this discussion, we are remembering the pioneers of quantum mechanics. De Broglie, he told particles can behave like a wave. Schrodinger, he developed a quantum mechanical model of an electron that treats it like a wave. Heisenberg, he stated the principle it is impossible to measure the momentum and position of electron exactly at the same time. In all these discussions, the important varied behavior of particle can behave as a wave also. Before going to this discussion or this idea, particle can behave like a wave. So the idea behind this one is dual nature of light. So we will discuss about dual nature of light first. Then we will analyze the hypothesis given by de Broglie, that is, particle can behave like a wave. So coming to the dual nature of light, it behaves like a particle as well as a wave. But if you discuss about the concept of particle, it is a physical object. It has mass. It occupies a small area in the space and easy to locate also. And it is specified by velocity, energy, and momentum. But coming to the concept of wave, for the wave, the propagation of disturbance through the space and time. It occupies large area in the space, so very difficult to locate. And it is specified by the frequency, phase, and wavelength. So if you observe these two concepts, particle and wave, quite different from each other. And assigning both the nature to same system is a contradictory idea. Cannot be acceptable actually. But we have assigned light exhibits dual nature. Why? Because if you observe the phenomena exhibited by the light, for example, interference, diffraction, polarization, all these phenomena are successfully explained only by the wave nature. But if we take the phenomena of photoelectric effect and Compton effect, these are also exhibited by the light beam only. But these are successfully explained only by the particle nature. But all these phenomena are exhibited by the light beam only. But some are successfully explained by the wave nature, some are successfully explained only by the particle nature. That's why Einstein finally concluded that light can exhibit both the natures, but it cannot exhibit both the natures simultaneously. With this idea, de Broglie has given hypothesis. That is, nature loves symmetry. So in the nature, everything is symmetry. So in case of light wave, it behave like a particle. So that's why particle can also behave like wave. That's why he has given a hypothesis, that is, waves are associated with moving particles. So what is the de Broglie hypothesis? Waves are associated with moving particles and their wavelength lambda equal to h by mv. So what is the h here? Planck's constant, and m is the mass of the particle and v is the velocity of the particle. And these waves are named as matter waves. These waves are named as matter waves. And the wavelength is known as de Broglie wavelength. How he has given this formula? The idea behind getting this formula is also due nature of light. We know the energy in case of light beam propagated as a energy packet, those packet is known as photon. And the energy of the photon E equal to h nu. And we know mu equal to c by lambda, velocity of light by wavelength of. And when the photon comes to rest, the rest mass of the photon is 0. So when the photon comes to the rest, that mass is converted into energy according to Einstein mass energy relation E equal to mc square. So if you equate these two formulas here, then mc square equal to hc by lambda. So now this is c square cancel here. Therefore lambda equal to h by mc. Here m is the mass of the photon and c is the velocity of the photon. So m into c gives the momentum of the photon. So here p is the momentum of the photon. Therefore, the de Broglie wavelength associated with a photon is lambda equal to h by p. That p is the momentum of the photon. Same thing if you apply for particles here. The p is replaced with mass into velocity in case of a particle. So in case of particle, the de Broglie and the lambda equal to h by mv. That momentum equal to mass into velocity of the particle. He just has given the hypothesis, but he has not given any proof for it. So there is no experimental evidence for matter waves given by the de Broglie. But the first experimental evidence for matter waves is given by Davis and Germer. He did an experiment. In that experiment, he supported what are the results he got. Based on that one, he supported the de Broglie hypothesis. What the experiment he has done? He has taken an electron gun. From that, we are getting an accelerated beam of electrons. Those are focused onto the nickel crystal. The reflected electrons are identified by means of a Faraday tube. So the concentration of reflected electrons are measured by Faraday tube, and this Faraday tube is moved at different angles and measured the reflected intensity of electrons from the nickel crystal. And he plot a graph between the angle and intensity of electrons reflected. But what he have observed in that case is he observed that pattern is a diffraction pattern. So here we are focusing beam of particles, but we are getting a diffraction pattern. So diffraction is the phenomena that can be exhibited by the waves only, not by the particles. But here the beam of electrons are exhibiting the phenomena of diffraction. That is possible only when waves are associated with these moving electrons. In this way, the Davis and Germer supported the de Broglie hypothesis. In the similar way, one more experiment is done by G.P. Thomson. In his experiment, he focused accelerated beam of electrons onto gold foil here. In the previous case of Davis and Germer experiment, the electrons are accelerated around the 100 to 300 volts. But in this case, the electrons are accelerated through a potential difference of 10,000 volts to 50,000 volts. And those are focused on the gold foil. And the scattered beam is collected on the screen. Again, they observed a pattern of dark bright, concentric rings. This pattern is again diffraction pattern. So a beam of electrons focused on the gold foil but the output we are getting a diffraction pattern. We know diffraction is the phenomena exhibited by the waves only, not by the particle. So G.P. Thomson also supported the de Broglie hypothesis. And after that, we are going to discuss about the expression for de Broglie wavelength in terms of kinetic energy of the particle. According to de Broglie hypothesis, the wavelength lambda equal h by mv. We know the kinetic energy of a particle of mass m moving with velocity v is half mv square. So multiply on both sides with 2m and take the square root, then root 2m ek equal to mv. So if you multiply on both sides with 2m, then you will get 2m into e, that is ek, that is kinetic energy. So then this side, if you multiply the 2m, then what happens? 2 will cancel. Here we are getting the m square v square. Then square on both sides, we will get root 2m ek equal to mv. Then we replace this mv with 2m ek. Then you will get the expression for de Broglie wavelength in terms of kinetic energy of particle. So lambda equal to h by root 2m ek. If a charged particle of charge q accelerates through a potential difference of v volt, then what is its kinetic energy? The kinetic energy ek equal to q into v. Then what is the de Broglie wavelength of a charged particle? Accelerates through a potential difference of v volt. We have replaced ek with q into v. Then the formula is lambda equal to h by root 2m q into v. If you want to find the de Broglie wavelength associated with an electron, then in the case of electron, this m becomes mass of the electron and this q becomes charge of the electron. And we know the h is the Planck's constant. By substituting these values in this formula, you can get the de Broglie wavelength associated with an electron when it is accelerated through a potential difference of v volt. So that we can obtain like this. So take the h value as 6.625 into 10 power minus 34, and mass of the electron is 9.1 into 10 power minus 31 kg. Charge of the electron is 1.602 into 10 power minus 19 coulombs. And we know h is Planck's constant. Its value is 6.625 into 10 power minus 34 joule Kelvin. So by substituting all those things here, then you will get the de Broglie wavelength associated with an electron is root 150 by v angstrom units. This v is the accelerating potential. So this is the expression only applicable for electron only. That is lambda electron equal to root 150 by v angstrom units. V is the accelerating potential. Now we will have a look on what are the important properties of matter waves. These are associated with the moving particles. That means matter waves are associated with all moving particles. And these are non-mechanical nature. That means they don't need any medium for propagation. They are non-mechanical in nature. And if the lighter the particle, greater the wavelength associated with it. That means if the mass is low, the wavelength is high. Because here lambda equal to h by mv. So m is low, then lambda is high. So that is one of the important characteristic. Next, if slower the particle, greater the wavelength. So the velocity of the particle is low, then also wavelength is high. And they are charge independent. That means they are associated with all moving particles. They are not dependent on charge. They can associate with electron, they can associate with moving protons, and they also associate with moving neutrons also. They are associated with all moving particles. And they induce uncertainty in the position of the particle. Because of association of wave with moving particle, it is very difficult to locate the position of the particle. That's why they induce some uncertainty in the position of a particle. That uncertainty can be analyzed by using Heisenberg uncertainty principle in the coming lectures. And another important characteristic of matter wave is the velocity of matter waves is greater than velocity of light. The velocity of matter waves is greater than the velocity of light. How it can be proved simply like this. You see here. So if you take the energy E equal to h nu, in this case I mentioned as a frequency f. So E equal to h into f. And we know frequency is nothing but velocity by wavelength. So here W is the velocity of matter waves and lambda is the wavelength of the matter waves. Therefore, E equal to H into W by lambda. And according to Einstein mass energy relation, E equal to mc square. So equate these two, then mc square equal to hw by lambda. Then mc square equal to h, we know lambda equal to h by mv. So by substituting lambda equal to h by mv here, then we will get the mc square equal to h m w v by h. Then this m will cancel here. Then h will cancel here. Then you will find w equal to c square by b. So w equal to c square by b. We know v is always less than c. That means the velocity of the particle is always less than velocity of light. So it is impossible to achieve the velocity equal to velocity of light or more than velocity of light. That's why v is less than c. Then definitely w is greater than c. In this way, we can prove that the velocity of matter waves is greater than velocity of light. So now we are going to discuss about two important parameters related to these waves. The first one is phase velocity. So what is the phase velocity? See, if you take a wave here, if I observe these points, if you see this point and this point and this point, the 3 points are the points in the same phase. And these are the points which are in the same phase. Again, these are the points in the same phase. So these points will occupy same position in the equal time interval here. So their velocity is constant. So the velocity with which constant phase points are moving is called phase velocity. So the velocity with which constant phase points are moving is called phase velocity. So if you take a general wave equation, this is given by D'Alembert. The general wave equation of wave is dou square y by dou x square equal to 1 by v square and dou square y by dou t square. Here, v is the velocity of the wave. So when the wave is propagating with velocity v, then what is its equation of motion? Its equation of motion is given by dou square y by dou x square equal to 1 by v square into dou square y by dou x square. So the solution of this one can be written as y equal to a sin omega t minus kx. Here, y is the displacement at any instant, and a is the amplitude, and omega is the angular frequency, k is the propagation constant, that k equal to 2 pi by lambda, and omega equal to 2 pi into f. And here in this case, this omega t minus kx is called phase. What is this value? Phase. So the velocity with which these constant phase points are moving, these constant phase points are located with x here. How x change with time, that is dx by dt, gives the phase velocity. Dx by dt gives the phase velocity. So the velocity with which constant phase points are moving is called phase velocity, that can be obtained by differentiating this phase here. We know phase remains constant for these points. That's why differentiation of constant equal to how much? 0. So the d by dt of omega t minus kx equal to 0. If you differentiate this one and simplify, you will get the omega by k equal to dx by dt. So this equal to v phase. So the phase velocity of a wave is given by omega by k, where omega is the angular frequency and k is the wave number or propagation constant, k equal to 2 pi by lambda. So therefore v phase is equal to omega by k. There is another important parameter we have to know about the wave associated with these moving particles, that is group velocity here. What is the group velocity here? If you take a particle moving with some velocity, if there is a one wave only associated with that one, then its momentum can be measured exactly. That means precise momentum we can measure by using the formula P equal to h by lambda, because we know according to de Broglie hypothesis, lambda equal to h by p. So lambda equal to h by p. Therefore, P equal to h by lambda. Therefore, P equal to h by lambda. So if only one wave associated with a moving particle, then we can measure the precise momentum of that particle. But it is impossible to measure its location. So if you want to localize, we can consider there is a superposition of two or more waves which are having slightly different in wavelength. So if you take the two or more waves like this here, they are slightly different in wavelength. See here, the crust and troughs are not matching here. That means they are slightly different in wavelength. Such a waves are superimposed, then the resultant is called a wave packet. So this is the wave packet. So in this way, we can localize the position of this particle. The uncertainty in the position of this particle is around delta x. So this wave packet, if you observe here, in this wave packet, the amplitude variation is changing with the position to position. That means the amplitude variation transmits along this wave packet. The velocity with which this amplitude variation transmits is called group velocity. The velocity with which amplitude variation transmits along this wave packet is called group velocity. To obtain the formula for this one, let us consider two or more waves which are having the slightly different in wavelength, means slightly different in frequency. Because we know the wavelength and frequency are related. The wavelength equal to c by nu, or frequency equal to the velocity of wave by wavelength of the wave. So let us take two waves which are slightly different in wavelength. So take y1, a sin omega t minus k. So here there is slightly different in wavelength, means there is slight difference in omega because frequency changes. There is slight difference in k because k equal to 2 pi by lambda. So the change in this frequency we can consider as delta omega. The change in k we can consider as delta k. Then by another wave which are having slightly different in frequency, you can consider as a omega plus delta omega n t minus k plus delta k into x. So if these two are superimposed, then the resultant is equal to how much? Y1 plus Y2. So this is the case. Then here if you take A common, then you will get sin C plus sin D. So if you apply the sin C plus sin D, that is equal to 2 sin C plus D by 2 into cos C minus D by 2. By applying this one, we can get this one. So here, when compared with this 2 omega, the delta omega is very, very less. So we can neglect this one. By compare with this 2k, this delta k is very, very less. We can neglect. But here we are having only delta omega, delta k that we can't neglect here. So by neglecting this one, we will get the 2 omega t minus 2kx. In both the cases, if you take 2 common, then 2 will cancel. Then you will get 2a into sine omega t minus kx into cos delta omega t minus delta kx by. Okay. In this term represents the actual wave. That's why we can take sine omega t minus kx is the main term here. That explains the resultant wave packet. And this one gives the amplitude of the wave packet. So in this case, what we have observed here, this amplitude also varies. So amplitude not remains a constant here. So this amplitude also varies. So that variation speed, if you want to find out, the velocity of this variation will depends on with what velocity this term changes. This is given by delta omega by 2 by delta k by 2. So then the velocity with which the amplitude variation transmits along the wave packet is given by delta omega by 2 by delta k by 2. So the 2 cancel delta omega by delta k. That can be written as d omega by dk. Therefore, V group is equal to d omega by dk. In the next class, we are going to discuss about the relation between group velocity and phase velocity and Heisenberg uncertainty principle. Thank you.